I spy with my little eye something that's blue. Yep, the ocean. You win again. This game is getting kind of boring. Hey, a message in a bottle. Dear Tim and Moby, my mom said you might get this message if I put it in the ocean. How can this happen? From Vivian. Vivian, does your mom know that we got shipwrecked? And that we've been drifting around aimlessly for a week? Please tell your mom to call the Coast Guard. I'm extremely hungry out here. What do you mean she doesn't know? She's asking about ocean currents? All right. The waters of the world's oceans are always on the move. Ocean currents help ships, animals, and bottles move around the globe. The ocean can be thousands of meters deep, but surface currents only affect the uppermost 100 or 200 meters of water. Fortunately, I brought my map of ocean surface currents with me. If you look closely, you'll see that the currents actually move in large circular patterns called gyres, and each gyre is bordered by one or more continents. Surface currents are mainly caused by wind. You might not know this, but some winds blow across the ocean in the same direction all year round. The rotation of the Earth causes the winds to deflect off to the right in the northern hemisphere and deflect off to the left in the southern hemisphere. This is called the Coriolis effect. That makes gyres rotate clockwise above the equator and counterclockwise below it. Surface currents have a major effect on climate and weather conditions. If you look at the map, you'll see that Paris, France is at about the same latitude as Montreal, Canada. But winters in Paris are a heck of a lot nicer than winters in Montreal. Parisians can thank a current called the Gulf Stream for that. It delivers warm water from the tropics to Western Europe. In the North Atlantic, the Gulf Stream radiates heat into the atmosphere. That's why the winters are warmer in France. Currents can make for colder climates too. Hawaii is located in the tropics, but its climate is slightly cooler than other tropical locations since the California current brings cool water south. Yeah, it'd be nice if we drifted ashore in Hawaii. Anyway, deep beneath the ocean's surface, there's another current system. It's not powered by wind at all, but by temperature and density. Remember the Gulf Stream? What are you talking about? I just described it like 30 seconds ago. Well, like I said, in the North Atlantic, the warm waters of the Gulf Stream radiate heat into the atmosphere. This loss of energy causes the water to cool off until it's almost freezing. Cold water is denser than warm water, so the surface water soon begins sinking. Millions of liters of water sink in the North Atlantic every day, but they can't just pile up there. They have to flow somewhere else. So when the cold water gets 2 or 3 kilometers down, it starts moving south. It flows all the way to Antarctica, then starts flowing north again. In the Pacific, the water starts warming up and returns to the surface. It flows back into the Atlantic Ocean, where it joins up once again with the Gulf Stream. And once the Gulf Stream waters reach the North Atlantic, they lose heat and sink, and the whole process starts over again. Because this current system loops all the way around the globe, it's sometimes called the global conveyor belt. The belt moves very slowly. It can take 1,000 years for water to make the full circuit around the Earth. Land! Moby, we're saved! Woo! We made it! Oh, drat.
All right, these are your notes on ocean currents. First, we're going to start with two types of currents. There are surface currents and deep currents. And we're going to start with surface currents. Surface currents are ocean currents that occur at or near the surface caused by wind. And the strongest surface current is the Gulf Stream. So you're going to want to highlight the Gulf Stream. There are three factors that affect surface currents. They are continental deflections, the Coriolis effect, and global winds. first we're going to start off continental deflections, and this is when surface currents meet the continents, the currents are deflected and change direction. In other words, when a surface current gets closer to a continent, it turns. In the southern hemisphere, it turns to the left. In the northern hemisphere, it turns to the right. So as you can tell over here, where this equatorial countercurrent, northern hemisphere, okay, and then the southern hemisphere. So as you can tell, as they get closer to the continent, it turns. So currents change direction when they meet continents. The second type of factor that affects surface currents are the Coriolis effect. And just like winds, these currents are deflected from a straight path due to Earth's rotation. So in the northern hemisphere, the currents deflect to the right. In the southern hemisphere, they deflect to the left. We've talked about that with winds. Well, ironically, currents do the same thing. Okay, and then the third type of factor that affects ocean currents are global winds. So we talked about our global winds in our last mini lesson on winds. Well, those winds actually affect our global surface current. So whatever direction a wind travels, the surface currents travel. So if you look on the left map, you can kind of see the direction that some of the currents are going, and then you can also compare it to the winds. They pretty much travel in the same direction. So winds that blow across the surface of Earth's ocean push water across Earth's surface. Most global flow in a similar pattern as the Earth's global winds blow. See the diagrams below. Okay, so let's take a look at this clip from the JASON project that kind of shows this global ocean conveyor circulation. Notice how the water travels, and they'll point out a little bit about how the wind travels.
Warm surface water flows from the tropics toward the poles. Cold, salty water forms on both sides of Greenland in the North Atlantic. This water sinks, forming the North Atlantic deep water current. This cold density current creeps south along the western side of the Atlantic, eventually meeting up with other cold, deep currents that form near Antarctica and circle the continent. From the Antarctic, some cold water loops up into the Indian Ocean and some loops up into the Pacific Ocean. Just like a conveyor belt, the cold, deep currents in the Pacific and Indian Oceans come up to the surface and join the warm surface currents. A major warm current crosses the Pacific from east to west, enters the Indian Ocean, wraps around the tip of Africa, and then crosses the southern Atlantic Ocean. This warm surface current eventually meets up with the Gulf Stream and moves along the east coast of North America before moving off toward northern Europe.
So next we talk about what powers these surface currents, okay? Surface currents are affected by the uneven heating from the sun and winds. Therefore, the major source of energy that powers surface current is the sun. So no sun means no changing of winds, also means no changing of water flow or currents. So now we go from being surface currents, we talk about what's underneath the surface, and these are deep currents. As you just watched in the video, some of these surface currents actually cool and sink and become deep currents. So deep currents are ocean currents that occur far below the surface, caused by differences in temperature and density. So if you remember in the past, we had talked about density and how cool air sinks and warm air rises. So therefore, cool air is more dense and warm air is less dense. Okay, well, that concept also applies to water. So when water cools, okay, that water is going to sink. So therefore, cool water has a high density, so it sinks. Unlike warm water, has a low density and it's going to rise. Deep ocean currents also form due to something called salinity. and it's the measure of amount of dissolved salts or solids in liquid. So if you actually took a gulp of surface water versus a gulp of deep ocean current water, the surface water would actually be less salty. And I know, like, that's comical because it's disgusting, but it actually would be less salty than what it is in the deep currents. That's because in deep currents, high salinity means it has a lot of salt, so therefore it's going to sink because it has high density. Unlike low salinity, has less salt, so therefore it's going to be less dense, so it rises. So the idea is that warm water or low salinity water is less dense, so this water rises above the deep current water. Cooler and more salinity water is more dense, so this water sinks below the surface currents. So this is very similar to how convection currents occur, and actually it's related to our deep currents. With these two currents, whether surface currents and deep currents, they're linked together. They form a convection current. The surface currents act like a conveyor belt. Oh, sorry. So the surface currents act like the top part of the conveyor belt. Let's change this. Top part of the conveyor belt. Let me fix this. And the deep current acts like the bottom part of the conveyor belt. When the water surface absorbs the energy from the sun, the surface currents carry this energy to cooler regions. When it cools, it sinks to the deep currents, allowing this water to travel along the ocean floor. So watch this video clip from the Jason Project on how this is supposed to look.
The AUV collects information like salinity and temperature at different depths, and scientists care about these measurements because they determine water's density and therefore the way the ocean water moves. That's because colder water is denser, so it sinks below warm water, and more saline or salty water is denser and sinks below fresher water.
So just like in the video you watched, you should have, if you have a paper version of this, yours would be in black and white. So it'd be probably the best for you to actually color in the different arrows on your paper. So these bottom arrows are going to be blue. Okay, they're along the bottom of the ocean floor. So on the deep currents, these are going to be cooler. And eventually those deep currents will rise when it becomes warmer and become less dense, or if they lose some of its salinity and become less dense and rise. So that's why these arrows toward the top part, like the conveyor belt, are going to be red to signify warmer waters. And then here in this area here, you're going to visualize it where the red is going to go down and it's going to turn blue because the red warm water eventually will cool down or gain some salinity. So finish drawing that picture into your notes if you're doing it on paper. Otherwise, let's go ahead and move on to something called upwelling. Upwelling is not an easy concept to understand because we are not near an ocean, so we don't see much of this. But if you stood on the coast of an island, you'll notice that the water gets pulled out to sea, and that's because it's caused by the wind. So near our west coast, air is caught. The upwelling near our west coast causes air to move away from the coast, and this what happens is when you pull that water away, then new water can take its place. In fact, that new water is going to be nutrient rich water, cooler nutrient rich water. So this acts to pull up high nutrient water from deep down to the surface. And that upwelling means that there are nutrients for plants and animals to thrive. So you'll actually have organisms hide out near the coast so that they know the wind's going to pull some of this warm water away and bring up cold water to the coast with some food for them to eat. So all in all, there's important reasons why the water or the oceans have to move, and that's because they transport different things, okay? First one is obviously to transport water. So the water never sits still. Along with the moving water, it transports gases. So oxygen, carbon, and nitrogen. It's actually a good reason why organisms like fish, they constantly have to be moving in the ocean because it's the only way the water goes through their gills and oxygen gets filtered out. Currents help transport that new oxygen from one place to the next so that these organisms have something to breathe on. They also transport dissolved solids, such as nutrients and food. And also, finally, they transport energy, specifically thermal energy. Sometimes even organisms require these currents to transport themselves. In the movie Finding Nemo, it actually shows a great example of how organisms such as turtles travel from one place to the next on something called the EAC, the East Australian Current. That's a real thing. And you do have turtles that travel on it as well as other schools of fish. So no currents means these organisms won't travel to different places around the world. So that's the end of your current notes. You can go ahead and hang on to those. And then the last set of notes that we're going to go over next are our climate notes.